If you recall the limitations of an acid-catalyzed hydration reaction, there could be two potential problems. First, you always get the Markovnikov product, and second, you can get a carbocation rearrangement. We've dealt with the issue of carbocation rearrangement using an oxymercuration demercuration reaction, but how do we deal with the problem of the Markovnikov product? One way we can do that is change the reaction conditions for a hydroboration oxidation. This, just like a hydration, adds water across a pi bond, but this allows for an anti-Markovnikov addition. Again, it's an electrophilic addition reaction. In this case, we're using borane, BH3, to add boron into the molecule, and then we will oxidize that to convert the boron into a hydroxyl group. How does this work? Well, if we take our alkene, again, we have the alkene pi bond acting as a nucleophile. Boron is an excellent electrophile because it only has 6 valence electrons in BH3, which means it has an empty p orbital that can accept electron density. After the nucleophilic attack, we again generate a carbocation, in this case in the more substituted site. Because the boron gained electron density from the pi bond, it now has a negative charge. If you compare this to a hydration reaction, we're adding boron normally where we would see a hydrogen atom. After this occurs, because the boron has a negative charge, it needs to shed some electron density, so we'll have a hydride shift from the boron to the carbocation. This will eliminate the charge and will eliminate the carbocation as well. Now we have this borane species, which we can oxidize using hydrogen peroxide and sodium hydroxide to convert into an alcohol group. Notice now we've added the hydroxyl group at the least substituted position. This gives us an anti-Markovnikov addition. An important consideration for this type of reaction is that it will give you a syn addition and will generate racemic mixtures. Well, what do we mean by a syn addition? Well, remember, what's being added in this reaction is a hydrogen and a hydroxyl group. Whenever these are added to a double bond in a hydroboration oxidation, they're always going to be on the same face. Notice this hydroxyl group is a wedge, as is this hydrogen. This doesn't mean we get the cis or trans form of the product, but the hydrogen and the hydroxyl group are always on the same face. We can also see that it could be wedges for both of them. So why do we get a racemic mixture? Well, let's take a look at our species here. Let's rotate the alkene a little bit so it's a little bit flat. Now we're going to add in our p orbitals, and you can see that there are 2 sites where the borane can coordinate. We're going to write the borane as BH2 with a hydride attached. Okay, the alkene can attack the borane, and notice the hydride is on the top of the molecule, just like the boron is. So when the hydride comes down, it will be on the same face. In this case, they'll both be up, we would call a wedge. Alternatively, if we had the borane on the bottom end of the molecule, when the alkene attacks, the hydride will shift to the bottom as well, because the hydride is tethered to the boron atom. So in this case, we get a racemic mixture because each of these is equally favorable, but we're always going to have a syn addition. So to summarize, hydroboration oxidation reactions proceed via an electrophilic addition mechanism, except the fact that the nucleophile is attacking the boron atom instead of a hydrogen. These will again add water across a pi bond, but unlike the other reactions we've seen, this forms the anti-Markovnikov product. The hydroxyl group will be at the least substituted site. This will again result in the formation of a racemic mixture, but the hydrogen and the hydroxyl group which are added to this molecule, the alkene, will always be in a syn addition, so they will be on the same face.